So given that, I'd like to now demonstrate how we download or how we program the microcontroller unit with the fuzzy logic controller and how we can validate that in real time. So what I have here is an example. So this is not the motor example that Talib was showing, but it's a slightly different one. So this system here has nonlinearity in it now. So we have essentially linear portion, a transfer function here, which is a pretty high steady state gain of 10, and then as well there's a dead zone. So the control effort will have no effect on the dynamics when it's within this minus 0.3 to 0.3 range. It's quite a large. It's maybe somewhat artificial, but it'll show the power of the fuzzy controller. So this is being tuned already, and you can see here this is the unit step response. So excuse me, the blue is the process variable, and this brown is the control effort. And you can immediately see how nonlinear the fuzzy logic controller is. It starts off very high, very strong output to drive the process quickly to the set point, but it's intelligent enough to know that it has to break it quite dramatically before it overshoots, and so it settles nice and quickly and smoothly to your set point. So what we'd like to do now is put this fuzzy logic controller onto our chip and see how we can validate it from there. So to do that, in this other example, in this other project here, what I've done is I've taken just that fuzzy logic controller block, isolated it, but this is the same fuzzy controller. And I've used these small terminal blocks to sort of define the I/O points for this controller. So the controller takes two inputs. You tell it the set point, you measure the process variable, and it will compute your control effort or control output signal. So the idea is this small block diagram now represents our controller, and we're basically going to program that onto our chip. So the chip is currently connected, or the FLC board is now currently connected to my system through my USB cable. So if I open the relevant dialog here, I can communicate through the COM port, and it's just a standalone FLC board, which we call the XCM. And when I connect to it, this basically shows you a map of what's available on the chip, how much flash memory is available, where you can store your parameters, et cetera, et cetera. So right now, this is an empty chip, basically. So what we want to do is program these controller parameters onto the chip. So I'm going to choose one of the regions of memory here, give it a small description, my FLC. This controller here was developed for a 0.1 second execution interval. So we have to tell the hardware we want to run it every 100 milliseconds. And now I program the chip. And now that the chip stored in the memory has the controller. And you can see here it's got two inputs, one output, and here are inputs and outputs and their ranges. So this is now a ready to go controller. Now typically if this were connected to a host application with a real system, you could actually try running the full loop and monitoring it to see how it performs. But before you do that, there's an intermediate validation step you can do where you can actually run this controller as a hardware in the loop and use the edeX software to simulate your process response and see how it behaves. So to do that, let me just disconnect here. And this other project I have here, oops. So this diagram now is the opposite of the controller diagram. It only has the process model blocks. So here's our transfer function that we had and our dead zone. So we're telling the edeX software now, I'm going to give you the control output, and you're going to compute how the process would respond. This is all in software. So if I connect to my controller board again, you see here the fuzzy logic controller is still in a non-volatile memory. And I can go to my controller testing tab and tell the edeX software that I want to do a simulated closed loop control test. So basically now the controller is running on the hardware in real time, but the process model is running on the software. And then I basically connect the two together, saying that the PV input of the controller will come from this PV block, this PV signal here in the model, and the control output from the controller will be fed into the CO terminal block here and go into our process model. So now we've connected a closed loop, and I can open this window to start the controller test. So let's start with the unit step and see how it responds. You can also, if you prefer, or if you need to, you can save all this data, this real-time data, to log file for your later analysis and graphing. So here we start. And we can see in green the controller output, and in blue the process variable response, and the black is the set point. So just like in the pure simulation case, it reaches the set point smoothly and it holds there. And again, you can see the nonlinear behavior of the controller. Very rapid output near the beginning, and then it can break the response as it requires. So let's see if we go another 100% up. And we reach now the next set point. So you can see that this controller is fairly robust, and it behaves smoothly in real time as well as in the simulation. Let's see if we can bring it back down again. So here it's going basically to its lowest possible output and letting the process decrease. And then it sees that it's approaching quite fast, so it's going to give it a small burst of control effort to break it and make it smoothly reach the set point. So this is the essence of basically a real-time validation. I mean, the next step is to actually run it on the full external system, and they can still use the edeX software to monitor it at least and change set points, et cetera, et cetera. Okay, so that's essentially really what I wanted to show today. So I think this sort of covers the entire workflow from modeling your process to designing your fuzzy loop, and running it on an actual real-time hardware and validation. So thank you very much, and I'll send it back to